Hello everyone. Good afternoon to all my students in my YouTube channel. So today my topic is the continuation of the geometry classes. So our topic today is tangents and normal. So I have divided my chapter into two parts. This is part 1. Especially we'll talk about tangents in this chapter. So what do you mean by tangents? That will be the first question. Let us consider a non-singular conic second degree general equation of second degree ax squared 2hxy plus by squared plus 2gx plus 2fy plus c equal to 0. This is the general equation of second degree, or you can say this is a non-singular conic. And let p comma q be 2 points on C. P is x1 y1, q is x2 y2. The line through q and p is called a secant of C. Secant of C. So you see, if this is your point P is the point on the line, and Q is another point on the line, on the curve, the conic. So if you connect P with Q, this is your PQ. PQ is a secant, right? Now, if you change the position of Q, so if Q is approaching towards P, that is, this is the new position, then again, if you can draw the line PQ, if you join the P and Q, then you have a secant. So this so on. If you do the process, then you will find a line like this. This is called PT, the tangent. That means in the limiting case, as Q approaches P, the secant will in general approach a limiting position represented by the line PT. Then the line PT is defined to be the tangent to C at P. Then PT is the tangent to C at the point P. And the point P is called the point of contact of the tangent. So that is the concept behind the tangent lines. Okay. So it's actually the limiting case of the secant. Now you can see here, there are two diagrams side by side. So in the second diagram, you can see how Q approaches towards P. So the blue lines are the secant and the red line is the tangent at P to the curve, right? And this is how you can define the slope. M is equal to the slope of the tangent. You can calculate the slope of the tangent by the gradient or slope, and it is also measured by dy dx also. Okay. Now let us have a introduction of the tangent chapter. So we have defined tangent. Now suppose a line Lx plus My plus N equal to 0. You have a line and a non-singular second order non-singular conic given by equation 2. Now there are three mutually exclusive exhaustive relations between 1 and 2. What are the relations? Number 1, there is no common point. Number 2, there are 2 points in common. Number 3, there are only 1 point in common between them. Okay. So these are the three possibilities. So suppose if this is the curve, suppose this is the curve, this is the conic, and this is the straight line, then there will be no intersection, or it will touch the conic, or it will cut the conic at two different points. So that was the cases. So in case 1, the line doesn't intersect the conic. In case 2, the line intersect the conic at 2 points, and the line is called the secant of the conic. In case 3, the line touches the conic at the common point and is called the tangent to the conic at that point. So these are the three main cases if you solve a general equation of second degree and a line. So what you have to do? You have to eliminate x or y. Let us eliminate y, or let us solve 1 and 2 with the help of elimination. So I will eliminate y. So I will get the value of y from the first equation. I will substitute in the second equation to get the quadratic equation in x. Right? You look at that. After solving and manipulation, we are arrived at this type of equation. So we have eliminated, right? And m should not be 0. Your denominator should not be 0. So this is after simplification. This is the quadratic equation. Look at the quadratic equation. You have the quadratic equation in x. Now you want to solve the values of x, or you have to find out the roots of the values of roots of x. So for equal roots, you know the tangent lines touches the curve. The tangent line touches the curve. So there will be equal roots. Roots are real and equal. For real and equal roots, discriminant should be 0. So that will give you the condition for tangency. Now there will be three cases: either no real root, or two real and distinct roots, or two real coincident roots. So these are the main three cases, right? Two real or distinct roots and two real coincident roots. So in that case, this is less than 0, greater than 0, and equal to 0. These are the cases. So that is from the discriminant. So, and equal to 0 gives you the condition of tangency. Okay. Now I will find out, now I will find the tangent to the non-singular conic without using any differentiation. You can do the differentiation because you know the first order derivative will give you, at that point will give you the tangent, slope of the tangent. You can get the value of the slope of the tangent and substitute, you will get the equation of the tangent. So I am specially using the geometry in this sense. So this is your number one is a non-singular conic, and let the line be y minus beta. Actually you want to find out the tangent at alpha beta. So y minus beta equal to m into x minus alpha is the equation of the tangent at alpha beta. Now m is the only unknown. So let us eliminate y between 1 and 2. So you have again a quadratic. I am using the same logic here. So this is the quadratic in x. Now for equal roots, let alpha comma alpha be the roots. Then you know that sum of the roots is given by minus b by a. So using that, you will get the value of m. If you simplify, you will get the value of m in terms of alpha beta and the known coefficients a, g, h, b, f. So this is the value of m. The slope is given by this. So if you substitute, you will get the equation of the tangent. If you substitute in equation 2, replacing m, because m was the only unknown, you will get the equation of the tangent at alpha beta. And if you simplify further, for the point that alpha beta lies on 1, so this should be 0. This should be equal to minus c. So you will arrive at this type of calculations, and after some manipulations, you will arrive at ax alpha plus h x beta plus y alpha plus b y beta g x plus alpha f y plus beta plus c equal to 0. So this is the equation of the tangent at alpha beta. Now look at that. This is the elaborate process, the long process you have to go through. Now I will tell you the shortcut method how to identify the tangent at alpha beta. So you look at that, your square term is x squared, that is your x alpha, and a is the coefficient. Your product term is xy, that will be x beta plus y alpha, and 2h, so it will be halved. Your twice terms will be halved, and again your square term will be y beta, and your 2gx will be halved, g into, and x will be x plus alpha. Again your 2f term will be halved, that is f into y plus beta, and the constant remain as constant. So that is the logic behind how will you write the equation of the tangent directly from the curve. You have to write the equation of the tangent directly from the curve. Let's see. Let's see for a few examples. Let us have the equation of the tangent at x1, y1. So you have a squared term, x squared. So let us write directly. I want to write the equation directly without any calculation. Sometimes it is needed for any other calculation part. So ax square is ax x1, because I told you if there is a squared term, it will be x x1. And if there is a twice term, it will be halved. So h and xy, 2h will be h, and xy will be product term can be written as xy1 plus yx1, and square term will be again y into y1, product 2gx, that will be halved, g into x will be x plus x1, 2fy it will be halved, and f into y plus y1, and constant remain as constant. So this is the equation of the tangent at x1 y1. So with the same logic, using the same process, let us write some known geometrical curves in terms of the tangents. Let us write the tangent to the circle, x square plus y square equal to a square at x1 y1. So that will be x x1 plus y y1 equal to a square. You can write the parametric point, and you can write the equation of the tangent at the parametric point also, because for circles the parametric point is a cos theta, a sin theta, right? A cos theta and a sin theta, that is the parametric point, right? So you can write the tangent. So x1 plus y1 equal to a square, and tangent to the general equation of a circle, if you consider the general equation of a circle, that is x square plus y square plus 2gx plus 2fy plus c equal to 0 at x1 y1, you can write it like a general equation of second degree. X1 y1 gx of x plus a1 f y plus y1 c equal to 0. And if you want to write the parabola, for the parabola y square equal to 4x at x1 y1, that will be y1 equal to 2a into x plus x1. And if you want to write for the ellipse the same way, because square term will be product, you can write it directly without any calculation. And for the hyperbola also there will be 1 minus. So that is how you can write for different curves the tangent directly without any calculation. Now let us find the condition of tangency of a straight line to a circle. Let us consider the circle x square plus y square equal to a square, and the straight line be y equal to mx plus c. So let us solve these two, the line and the circle. So let me eliminate y between the two equations. So you have this quadratic equation in x. So for circle, for tangent, it must have equal roots. This equation must have equal roots. So b square equal to 4ac. If you apply b square equal to 4ac, the condition will be, you will get the condition. So this is the condition of tangency for a circle, right? And you can use that method also. What is the method? You can, for circle only. So circle, you have a center of the circle. Circle center is 0, 0, and the straight line is given by y equal to mx plus c, right? This is the straight line, and from center the perpendicular distance is the radius. So a is the radius, so a equal to the distance from 0, 0 of the line y equal to mx plus c. That will give you the same condition also. In that way you can get the condition for tangency for a straight line, for a circle. Okay, right? Okay, let's have a condition of a tangency of a straight line to a parabola. So you have a parabola. I'm considering the standard equation of the parabola y square equal to 4ax. So if you consider y equal to square equal to 4ax and the line y equal to mx plus c, again by elimination of y, or I want to, my target is to form a quadratic in x, or you can form a quadratic in y also, no problem. So after that, after this quadratic, your main condition for tangency is that if the line touches the curve, then the roots are real and equal. For equal roots, b square equal to 4ac is the condition, or b square minus 4 is equal to 0. So if you apply this condition here, you will get the condition for y equal to mx plus c to be a tangent to the parabola c equal to a by m. So this line will be a tangent to the parabola. Now let's have a condition for more things we have. You can write the tangent in the form of a slope form, because m is the slope. This is called the slope form of the tangent. So you can replace c by a by m. So this will be the slope form of, this is sometimes very useful. This is the slope form of the tangent to the parabola. Okay, and you can get the point of contact also, a by m squared 2a by m. This point of contact is also very important, because if you write the slope form, this will give you the point of contact of the tangent. And let's have a condition of tangency for an ellipse. So if you have a condition tangency for an ellipse, x squared plus a square plus y square by b square equal to 1. Again, if you want to eliminate, and you have to form the quadratic equation. This is the quadratic equation after calculation. So again, you are applying b square equal to 4ac for equal roots, or the tangents for real roots, real and equal roots. Okay, so if you apply, you will get this type of relation. This is the condition of tangency for a line y equal to mx plus c to be a tangent to the ellipse. And if you apply for hyperbola, you will get, okay, Let me give you the slope form of the ellipse or tangent also. This is the slope form of the tangent for the ellipse, and you can get the point of contact in this case also. This is the point of contact. And for the hyperbola, there will be one minus if you do the same calculation. So this is the condition of tangency for a hyperbola. Okay. So these are all about your condition of tangency for circle, for parabola, for ellipse, for hyperbola, and also their slope forms and also the point of contact that might be needed in somewhere. So let's have now concept of pair of tangents. What about the pair of tangents? Let's have a theorem first. From an exterior point x1, y1 of a non-singular conic, two tangents can be drawn to the conic. You can draw two tangents maximum. And the equation of the tangents are given by s1 equal to t square. It's a very important relation. You have to remember this relation, the pair of tangents from an external point, where s is the equation of the, or s is equivalent to this non-singular conic equation. Ax squared 2hxy plus by squared plus 2gx plus 2fy plus c. And s1, if you substitute the point in the conic, that is conic is satisfied by the point x1 y1, and t is the tangent at x1 y1. So you know, you have learned, that is why I taught you how to write the equation of the tangent directly from the equation of the curve. So your tangent will be ax x1 plus h into x y1 plus y into x1 plus by y1 plus g into x plus x1 plus f into y plus y1 plus c. So this is the tangent, right? This is the tangent. So I will prove, I will give you the result. Not only that result, I will give you the proof also, how to prove this result. So you have to remember the pair of tangents is given by this equation, s1 equal to t square. Now this is the pair of tangents for the circle. You look at that, this is the external point P, and you can draw two tangents. This is the point of contact with the tangent Q, and this is R. So this is suppose x1 y1 and this is x2 y2. You can say this is the, these are the pair of tangents from the external point P. Okay. Now let x1 y1 be the exterior point. The external point is x1 y1. Therefore it must the expression should be greater than 0 if you substitute, because the point is outside the conic. It is not on the conic, it is not inside the conic. So s1 must be positive, right? And let x minus x1 by L equal to y minus y1 by m be a line. You can write the line in this form also. Be a line through x1 y1 in the symmetric form. You can write the two-dimensional line for in this form also. Its parametric equations are, if you write this is equal to r, then parametric equation is given by x equal to lr plus x1 and y equal to mr plus y1, right? This is the parametric form where r is a parameter. So for any value of r, the point you will get the point, that point will satisfy the line anywhere. You can take anywhere, the point can be anywhere on the line. So r is a parameter. So any point on 1 can be taken as this, provided that lm not equal to 0. Both of them are not 0. Now the values of r for the common points. So you want to, my target is to solve. I want to solve for the conic and for the line. So with the help of the line. So the values of r for the common points of the line 1 and the conic is equal to 0 are given by this equation. So what I'm doing, I'm just substituting this point. This point will satisfy the conic. Okay, this is the common point for conic and the line. So I will replace x by lr plus x1 and y by mr plus y1. So if you substitute and simplify, you will get a quadratic in r. You look at that, a square r square plus br plus c. ar square, this is the quadratic, right? You can write the quadratic as ar square plus br plus c, capital C equal to 0. So this is the quadratic in r. You look at that, a is given by the first bracket and your b is twice curly bracket, whatever inside the curly bracket, that is b, and c is the constant term, right? And this should be 0 because x1 y1, no, x1 y1 is an external point, right? So and this is positive. If the line 1 touches the conic, there is only one point in common between 1 and the conic S equal to 0. Hence, both the values of R in 2 are the same. This is S1 actually. This is your S1, right? This constant term is your S1 because it is S is satisfied with X1, Y1. So if you, for both the values of R are the same, so you will apply B square equal to 4AC. You will apply B square equal to 4AC, right? So if you apply B square equal to 4AC, here you have a 2 also. So 4 cancelled from both sides. You will get this type of number 3. You will get number 3. After simplification, you will get number 3. And S1 is this one. This bracket is S1 actually. This is your S1, right? Now, so 1 is a tangent to the equation 1 is a tangent to the conic provided elements satisfy 3. Thus, any point on the tangent satisfies the equation. This one. So if you simplify, what is your L? L is, you look at that, your L is given by x minus x1 by R. Y minus M is y minus y1 by R. So if you substitute, R will get cancelled from both sides, eliminating Lm by 1. Actually, you are eliminating Lm by 1. You are using 1 to eliminate Lm. So you, in the equation 3, you have L and M everywhere. So you have to eliminate L replaced by x minus x1 by R, M replaced by y minus y1 by R, and R gets cancelled from both sides, no problem. So after that, you have this type of relation. So if you simplify further and manipulate your calculation, so you will get this type of relation, t minus s1 whole squared. And you know what is t? T is the tangent equation, and s plus s1 minus 2t s1. So if you simplify, you will get this. This is the hint for your calculation. You can do the calculation. You can try that calculation and check that this will be the final result. So what is the conclusion? The equation of the pair of tangents is given by s1 equal to t square. Okay. Now, this is the pair of tangents for the parabola. So if your equation of the parabola is y square equal to 4ax and the external point is p x1 y1, this is the external point, right? So what will be the equation of the pair of tangents? S1 equal to t square, right? That you have learned here. Yeah, look at that. So let me write directly. I will write directly somewhere. I don't want to do the calculation. Maybe you need this calculation for other purpose. So y squared minus 4ax, that is your s, and s1 is y1 squared minus 4ax1, right? And equal to t squared. T squared means the tangent, equation of the tangent. So y1 minus 4ax will be halved. So 2a into x plus x1 closed, brackets closed, and squared. So this is the pair of tangents, equation of the pair of tangents. If you simplify, you will get pair of straight lines. So your pair of straight line will be either second degree general equation or homogeneous. It can be, if it is a passes through 0, 0, then it will be homogeneous. So it will give you a pair of straight lines. Okay. Next, I will define. It's a connected with the director circle is connected with the pair of tangents. So that is why in my lecture today, I will describe director circle also. Actually, the definition of the director circle is the locus of the point of intersection of two perpendicular tangents to a conic is a circle. Then the circle is called the director circle of the conic. So if you find the locus of the point of intersection of two perpendicular tangents. So look at that. You have two perpendicular tangents. The tangents are perpendicular. So their point of intersection is P. So if this point moves in such a way that it forms a circle, then that circle is called the director circle. If it gives you a circle, then that will be the director circle. That will be the director circle. That is called the director circle. Actually, the locus of the point of intersection of two perpendicular tangents is called the director circle. This is for circle. You can get the director circle for the parabola also, for all others. Okay. So let's see how will you calculate the equation of the director circle. So pair of tangents from an external point x1 y1, let the point p be x1 hk or x1 y1. Then your pair of tangents is given by this, right? So I am applying S1 equal to t square. Look at that. You have applied S1 equal to t square for this circle. And if they are at right angles, this is, I told you that this will be the pair of straight line. So you know that if the pair of straight lines are right angle, what is the condition? What is the condition for pair of straight lines to be right angle? The only condition is that sum of the coefficient of x square and y square is 0. So if you take the sum of the coefficient of x square and y square, that will give you this one. Oh, okay, I will show you. Let me show you that part if you want to see. So okay, let me write this one once again. X squared plus y squared minus a squared, and you have x1 squared plus y1 squared minus a squared, right? Equal to, oh, minus, I have taken all the things here. So your tangent x1 plus y1 plus a squared. Okay, sorry, it will be minus a squared. Okay, just put minus here. Okay, minus a squared whole square equal to 0. So this is the equation of the pair of tangents, or you can say pair of straight lines, because tangents are lines. So if you simplify x squared into x1 squared plus y1 squared minus a squared, coefficient, I'm just considering coefficient of x squared and y squared, and y squared is also having coefficient x1 squared plus y1 squared minus a squared, right? And here you have also a one of the coefficient, that is plus or minus x squared x1 squared, and you have minus y squared y1 squared. I'm not calculating the rest of the part because I will consider only the coefficient of x squared, no other terms having x squared y squared, right? So you see that your coefficient of x squared is ultimately y1 squared minus a squared, and coefficient of y square is ultimately, after simplification, it will be x1 squared minus a squared. Yeah, and dot dot dot, all other terms you have xy constant and all other, I'm not, so this is equal to 0. So you must be remember that your pair of straight line will be this form: ax squared 2hxy plus by squared, and it can be passes through origin, or it can be 2gx 2fy etc. terms are there. So the lines will be perpendicular if and only, comparing with this, the lines will be perpendicular if a plus b equal to 0, right? So the coefficient of x squared and coefficient of y square, if you take the coefficient of x square and y square, you will get this one: x square plus y square equal to 2a square. You look at that, you have minus 2a square, and you will get 2a square here. So this is the, hence the locus of x1 y1 is x squared plus y squared equal to 2a square. This is called the director circle, the perpendicular tangents. Okay, locus of the perpendicular tangent. This is for the circle. You can get the things for the parabola also. Yeah, this is for ellipse. I don't think you okay, this is for ellipse. Ellipse, you have x square plus y square equal to a square plus b square. This is the equation. So for parabola, you have to check whether it exists or not. Okay, for parabola, you can check that the director circle exists or not. And for hyperbola, you have x square plus y square equal to a square minus b square. These results may be useful also. Okay, so this is the director circle for ellipse. You look at that, you have a director circle containing the ellipse, containing the rectangle, bounding box you have. These are the pair of tangents. This is the external point p x1 y1, and the locus of x1 y1 is the circle, and that is called the director circle of the ellipse. Now I will define chord of contact. Actually, you have learned that if this is the external point, here you have a as the external point x1 y1, then p and q are the point of contact with the tangent to the conic. So this, if you join pq, this is called chord of contact. This is called chord of contact, right? And we can show that the chord of contact is given by t equal to 0. That can be proved also, that we can show you the chord of contact is given by t equal to 0. You see, if you consider this circle, then your equation of the circle is x square plus y square equal to a square. And suppose P is the point x2, y2 and Q is the point x3, y3, right? So, the equation of the tangent at P is given by what will be the equation? X2 plus y2 equal to y squared, a squared, right? And equation of the tangent at Q will be x3 plus y3 equal to a squared, right? Directly. And you see this both the lines, if this P, the tangent passes through A, then you can write PA, the equation of PA. Actually, P, the tangent at P passes through x1, y1, so it will satisfy. So x1, x2 plus y1, y2 equal to a squared, right? And again, Q passes through, the tangent at Q passes through A, so you can write x1, x3 plus y1, y3 equal to a square. So from these two equations, you look at these two equations, x1, x2, y1, y2 plus a squared and x1, x3 plus y1, y3 equal to a square. From these two, we can say that these 2 points are satisfied by x1 plus y1 equal to a squared. And that is the equation of the chord of contact, because it will satisfy both the points. So the chord of contact is given by nothing but the tangent, like similar to tangent at x1, y1. So equation of the chord of contact is t equal to 0. That is why x1 plus y1 equal to a square. That is the proof. The equation of, so you have to remember the chord of contact is given by t equal to 0. Only you have to remember, because the relations, these two relations, this let me mark with the blue, 1 and 2, these two relations show that both x1, x2, y2 and x3, y3 satisfy the equation x1 y1 equal to a square. X1 plus y1 equal to a square. So this is the equation of the chord of contact, that is called chord of contact. Now, equation of the chord, this is the last thing to discuss about. So equation of the chord of the conic, which is bisected at x1, y1, and that is given by, the equation of the chord is given by t equal to s1. This is the chord of contact. So if this midpoint is known to you, that the midpoint is x1, y1, then the chord, equation of the chord is given by t equal to s1, where s1 is given, already we have mentioned, and t is the tangent. Okay, so equation of the chord of the conic, which is bisected at x1, y1, is given by t equal to s1. So you have to remember lastly 3 points. Your pair equation of the pair of tangents is given by s1 equal to t squared, and the equation of the chord of contact is given by t equal to 0, and equation of the chord of the conic, which is bisected at x1, y1, is given by chord of the conic, actually this conic, I'm talking about this conic, ax squared 2hxy, the general equation of second degree, that conic. So the conic is given by t equal to s1. So these three are very important and very new to you. You have to remember all these things. So that's all in this lecture, in the part 1. In the next lecture, I will describe mostly about the normal and co-normal points. So follow my lecture video and follow my YouTube channel. Thank you all of you.